Okay, so in the last class, we started discussing sequential circuits, uh, circuits that not only depend on the combination of inputs, which is typically the case for combinational logic, but it also, their output also depends on the history of the input. So basically, there is a feedback between the output and the input. So basically, the output could also serve as an input to these circuits. That is the big message, all right? So this is a history-dependent circuit. We looked at a block. We haven't even seen the circuit yet. We looked at a block called a latch, and I showed you the behavior of this latch. So apparently, there are two types, but let's start with one. This is a revision, of course, very quick revision. There was a signal called clock signal, which is more like a controller. And the block could be designed in a way that, by the way, you have a data and you have output. It This block could be designed in a way that only when the clock is activated or high or one, however you want to call it, only then the input will be sent to the output. Otherwise, when the clock is inactive or zero or low, output will remain as was. So basically, nothing will happen to the output as long as the clock is inactive. Okay? And we saw what this type of waveforms mean. This basically represents the input is changing. And just to show that the change could be either direction, like from high to low or low to high, we have this scissor-like waveforms that we typically draw. This is the typical approach towards drawing sequential circuit to make it general. Sorry. Okay, so to make it general, we try to draw it this way. Okay, and then the take-home message was, notice when the clock was activated, the input changes were reflected in the output. Clock activated, input changes reflected to the output. Otherwise, the output was stable. Notice that. When the clock was inactive, means zero, the output remained stable. Not fall, although the input was still changing. Notice that the input was still changing, but output didn't follow. That is the big message. Now, there are two kinds that we can make. One type that responds to the high or activated mode of clock, and the other one is exactly the opposite. That's why there is a circle at the clock terminal, because it is basically responding to the opposite version of the clock. So whenever the clock is inactive or zero, that's when the input goes to the output. All right, so that was the big message. There are two things that I don't think I mentioned explicitly, so I want to use these terms now because these are universal terms. We use them. So whenever the input is connected to the output, that means either clock high or clock low, depending on the type of the latch. That mode of operation is called the transparent mode. So get used to these terminologies and jargons that engineers use with each other. So is your latch transparent now? Yeah, sure, it's transparent. That means the input is sent to the output. And whenever the input is disconnected from the output, and that could happen for either clock equals 0 or clock equal to 1, depending on the type of latch, that mode is called the hold mode. Okay, so the latch that responds to the high level of clock, that's called a positive latch. And of course, the other one will be called a negative latch. So I hope now you understand the terminology. It's super simple. All right, so with that idea in mind, let's start taking a look at some circuits based on what you have learned so far. Okay, so in 433, there is a separate lecture on latch and flip-flop, and there we go even deeper into the specific circuits. But here we are trying to stay within the gate level. This is called the gate level. You're looking at a logic gate. What is this logic gate, folks? I hope you guys all remember this. It is a multiplexer or mux, right? You have seen this. I'm not showing you the transistor level details of it. When you go into the transistor level stuff, then there are additional concepts and uh, things that we need to discuss. But for this particular course, 255, we'll be staying within the gate level. We'll only look at the gate level circuits. Okay, so this is a multiplexer. Notice, I just want to highlight the similarity between what you have learned so far and the subtle change that made the circuit so different. Okay, so notice, a multiplexer uses a select signal. And if the select is if the select is 0, first input goes to the output. If the select is 1, the second input goes to the output. You all know this, right? But now, notice this mux is designed in a way that there is a feedback from the output to the input. So one of the inputs is basically the output. You see my point here? That is the only subtle change that we made. This is not an independent input. This is a input that is essentially a feedback from the output. And now what? So when the select is 0, notice that that's why it is marked so. When select is 0, this input goes to the output. When the select is 1, the corresponding input goes to the output, right? You see my point here? That's how it is marked. And this, instead of select, I can now call it a clock signal, because in actual chips, in actual circuits and systems, we use a signal like this, which, as I discussed, is like a clock. Its time period is fixed because we want to synchronize everything. And that's why instead of calling this a select signal, we call it a clock signal. Okay, but essentially, it is behaving like a select signal for a mux. It is selecting whether this input should go or the other input should go. And it is a very simple mux, folks. As you see, it's a 2-to-1 mux. It is choosing between whether to send the input to the output or whether to keep the output as was. Does that make sense? So, or unchanged. So it is taking a decision. Should I keep the output unchanged or should I send the input to the output? This is the only decision it is making. So it is a super simple mux, the easiest as it can be. Oh, by the way, how can if this is a negative latch, because it sends the input to the output when the clock is 0, how can I make it a positive latch? Just flip select signals, right? You design it in a way that 0 is here, 1 is there. So basically, whenever your clock is 0, then the output doesn't change. When the clock is 1, the output, input is sent to the output. Any questions or comments about this? So this slide is supposed to show you the simplicity and only the subtle change that changes a combinational circuit. This is a combinational circuit, essentially a mux, to a sequential circuit through feedback. All right, now we're going to take it one step further. So far, whatever we've seen, as of now, they're all latch, basically latch blocks. Okay, what a latch does is it basically, I don't know whether you caught it, it basically holds on to the output. That's why there is a mode called hold mode. It is holding the output. Uh, why would we need to hold an information? Let me be a little bit philosophical here, right? In digital electronics, you need to process digital bits, but you also have to store digital bit every once in a while. We call them memory, right? So will you buy an iPhone without a memory? Like, okay, when you select the specs, sure, you have this processor, that processor. The most important thing that you have to choose, you cannot choose much, honestly, in an iPhone. But the things that you can choose, among them would be the storage. Is it 128, 256, 512, or one? You get my point here, right? So the storage is basically memory. It is used to store data and not let them change randomly. You cannot just keep changing the data. You have to hold on to the data. See, I'm deliberately emphasizing the term hold here. So memories hold information. A latch, a simple latch like this, as long as it doesn't change the output, randomly change, it can hold on to the information. So it is essentially a memory. It is a different kind of memory versus the ones that we typically use and the ones that you get when you select 512 versus 256. That's not the type of memory you select, honestly. But this is a type of memory that is embedded in the logic portion. It is very close to the logic. Again, I'm not getting into the detail of it. It is such a broad field that I introduced a new course at UT called Advanced Memory Design, which I already taught twice. It's 400/500 level, so it's going to be a while. In case you are interested, you cannot take it right away. It's going to be a while until you can take it. But I'm just giving you a sense of how broad that domain is, that you have to set up a completely different course just to cover that memory side, right? So I'm not getting there. What I'm trying to allude to, that even though it's a super simple modification to a conventional combinational circuit, you basically create something called a memory. You create the concept of the memory for the first time. No other logic gate had memory, because the moment an input changes, the output will change right away. Okay, so they were so sensitive, but memories cannot do that. Memories have to hold on to the data, even if something changes here and there, unless there is a control signal that changes and that lets you change the memory. Okay, so keep that in mind. Now, we are going one step further. When you use a couple of latches and combine them in a certain way, you get something a little bit more interesting, and that is called a flip-flop. And here is what you get. Remember, a latch is a level sensitive circuit. It is sensitive to the level of the clock. Is the clock 1 or is the clock 0? That's what the latch cares about. But when you, so this is a latch. This is another latch. Okay, so notice one latch is driving another. There are essentially two latches. And this entire system is called a flip-flop. So a flip-flop is basically two connected latches. As simple as that. But are we going to connect them randomly? No. We're going to do an interesting trick here. Let me show you. Can anybody notice two differences between these two blocks that I marked? Yes. Thank you. Yes. I mean, to put it simply, your 1 and 0 positions have flipped. What that means is essentially one of them is a positive latch, the other one is a negative latch, as we just discussed, right? So this one will respond. What do I mean by this? I'll be using the jargons now. I hope you can understand this. This one will be transparent when clock is 0. You get my point here? When the clock is 0, input is sent to the output. So this one is transparent when clock is 0. This one is transparent when clock is 1. Okay, so that's why one of them is positive, the other one is negative, or positive. You see my point here, right? Okay, we typically use the term positive latch and negative latch here. Can anybody tell me which one is positive? This, let's call it A, and let's call it B. Which one is positive latch? A, thank you, yes. All right, so because this one responds to clock equals 1. All right, now, so this is deliberate, by the way. This is not random. You cannot just connect two positive latches or two negative latches. We use two different kinds. That's the reason why, when, remember, I told you, when, hey, there are two types of latches. One responds when the clock is high, the other one responds when the clock is low. We don't just make up a circuit, a mirror image to the other, just for the sake of fun, right? There are special agenda items that we have in mind. And this is basically the broad agenda. We are now making a flip-flop circuit by connecting these two mirror images together, essentially. By mirror image, I mean two different kinds of latches. Okay, now let's see how this circuit responds when the input and output changes. So imagine this is your actual input, data D. And since these latches are connected, the second one does not have any dedicated external input. It is being driven by the output of the first latch. Does that make sense? So you don't really control the input anymore. For the second latch, input is essentially the output of the first latch. So they are, of course, linked with each other. So when you think of it like a black box, you have one input, which is data D. You have one output, which is output Q. Essentially, you don't care about this intermediate output or input, whatever you want to call it, because you don't have any control over it directly. It changes by the dynamics of the circuit and the interaction of these two latches. Let's see how that happens. Okay. Excuse me. So I'll be using this timing diagram to explain it first. Take a look at this clock D and QM. Let's take a look at this three first. Essentially, if you forget about this second latch, isn't this going to be the exact same timing diagram as we discussed here, folks? This is just a latch, don't you think? So what I mean by that is, say clock is high here and the input is changing. Again, is this a positive latch or a negative latch? quickly? Negative, because it sends the input to the output when the clock is 0. So should it respond when the clock is high? Should the output get the changes of the input when the clock is high? No. So notice, this is your output. It is not changing. It is stable, even when the input is changing. But when the clock becomes 0 here, input keeps changing and the output follows. You see my point here? Okay, again, when the clock becomes 1, output stops responding. It goes into the hold mode. So hold, transparent, and so on. So isn't that a super simple repetition of what we already covered for the latch? Okay. So because that's what it is, essentially, it is a latch. But now that this output is basically the input of the second latch, let's see how the final output changes, the actual final output changes. Okay. Oh, sorry. Give me 1 second. Let me erase this. Okay, now for this guy, this is essentially the input. So your QM is basically the input for the second latch. And this is a positive latch. So it only responds when the clock is 1. So notice, this is where the clock becomes 1. This is the other point where the clock becomes 1. So we should focus on these 2 points for the second latch. Okay. So notice one thing. So QM changed here and Q also changed along with it. But then, see, QM changed or it remained unchanged, doesn't matter. Q basically didn't respond at all until when, folks? Until the clock became 1 again. You see my point here, folks? For that latch, it doesn't care what's the first latch is doing. It only looks at the clock and responds accordingly. So it responds again when the clock is high or 1. Okay. So basically, when the clock becomes 1, it sees some kind of change here at the QM and it follows that change. And then it stabilizes again. Now, I have 2 questions for you, unless you ask me first. I'm giving you the floor to ask me questions. Yes.
They just use, just keep one of them off the whole data. Just use one latch.
That's a great question. Why are we going through this trouble of coupling 2 latches, right? And there will be a big reveal. And you'll see the specialty of this circuit, honestly. I mean, what do we get? That's essentially my question to you as well, honestly. What are we getting by connecting these 2 latches, right? Okay. Can anybody see that there's a subtle change in the final output? There is something that changed. Okay, let me help you understand this. Take a look at these output, okay? So I'm gonna mark 2 regions here, region A and region B. Tell me, which region is transparent, A or B? B is transparent. How do you know? D is being transmitted to the output. So basically, that's when it is transparent. But when the latch became transparent, it kept changing with the input, don't you think? So the output is not stable. When it is transparent, it is following the input blindly. It's just doing whatever the input is doing. If the input keeps changing, your output will keep changing. It will not be stable. Okay. Now, take a look at this final output for the second latch. Okay, so when does it become transparent? Whenever the clock is 1. So that's when it should be transparent. But notice, okay, it is transparent. But do you see any, continuous changes here? Or is it always stable? It just has one transition. It reflects that, hey, something changed, and then it stabilizes. This is by design, by the way, it's not random. So this output, the final output, is more stable. It is controllable. It can be tracked. You have just one change and then it is stable. So as if you are filtering out the changes. You are allowing just one change at a time, just one change, and then stop. Change, stop. Does that make sense? Will a conventional latch allow you to do so? No, a conventional latch will keep changing. So the output is always driven by the input. But when you connect another latch back to back, the second latch will have a very stable output. It will only change once, if at all, if for some reason, imagine if the data doesn't change at all, like it is always stable, then nothing will change. You don't have any transition. But if the data keeps changing, your final output will only see one change, and then it will stable. It will be stable. Do you get it? Okay, so see the power of this. So essentially, can I use this comment as to this only looks at the edge of the clock, as if just look at the phenomena honestly. When there is a edge of the, what do I mean by the edge? When there is a transition, it is going from 0 to high. This is the edge of the clock. Again, 0 to high. This is the edge of the clock. Whenever there is an edge, it responds, and then it doesn't do anything. Are you all good? So essentially, by connecting two latches together, you have created an edge-sensitive system. So a flip-flop is an edge-sensitive circuit. A latch is a level-sensitive circuit. So it just cares about the level of the clock and then responds accordingly, keeps changing. Flip-flop responds to the edge of the clock. Whenever the edge occurs, it basically responds. And then, does that make sense, folks? Why is it useful? Okay, so if I want to keep track of every bit of data that is being passed through my system, okay, every bit of data, just look at the output. Which one is easier to keep track of and keep count of? Like, how many bits did I pass so far? 8. Okay, here is one more, 9. Here is one more, 10. In which situation it is easier to keep track of the bits that are being passed? With a latch or with a flip-flop, folks? What do you think? Right? Say here, if there is one more transition or one less transition with a latch, you cannot keep count. It's like randomly changing. But with a flip-flop, you have the full control. If you notice, you can count 1 bit, 2 bit, and so on. So basically, you pass 1 bit at a time in a system, and you can always synchronize it with the edge of the clock. You don't even have to count the output transition. You can count the edges of the clock. 1, 2, 3. So essentially, you have dealt with 3 bits. Just count the edges of the clock. But folks, can you count the level of the clock? You see what I mean? So, okay, so let's consider level. This is high level, high level. So you have 2 high levels. But do you know how many bits were transmitted during those 2 high levels? No, because it will basically keep changing as many changes as the input can provide. So it will keep changing all the time. You cannot keep count, but you can always keep count of the edges. 1, 2, 3. So there will be just 3 transitions, if at all. Does that make sense to you? As an engineer, do you think this is, don't you think this is an extra feature that you're getting by connecting these 2 latches together? Okay, now I have a question for you. As an engineer, if I ask you to design, hey, I don't want to work with positive edge. Oh, this is called positive edge because it's going from 0 to high. I like the negative edge. So I want to create a circuit, and I hope by now you have seen there is a philosophy of creating circuits that are kind of flipped version of each other. So if there is a flip-flop that responds to the positive edge, there should be a flip-flop that responds to the negative edge. So imagine I want to create a flip-flop that responds to this edge. Whenever the clock goes from high to low, it changes. How can you, like, what is your common sense tell you? How can you design that? Yes. Thank you. Yes. See, just basically just flip the latches. Put the positive one first, negative one later, you get the other one. So it's kind of like creating different shapes with Legos. Oh, what happens when you change this? Oh, okay, that's interesting. First, you can create different versions and people figure out ways to use them. So notice somebody decided to have 2 different types of latches and somebody else came up with an idea to put them together to create a circuit that is even more trackable, like a flip-flop, for example, right? That is even more trackable because you can keep track of the edges easier. It is easier to keep track of the edges. All right. All that I've told you so far is mentioned here. Positive edge trigger register. Oh, I haven't told you what register is. Question. Yes.
Just in this course, result from KUS and like algebraic simplification.
Mhm.
For it's going to be the timing line diagrams.
Great question. Yes. So since sequential circuit, as the name suggests, deals with sequences, timing diagram is a very big deal. You have never seen timing diagram for the combinational logics, did you? For n gate or gate, there was a truth table, which was the boss, right? We always had to look at the truth table because there was no concept of any sequence. As long as there is a combination, you have a certain output. But this is not just dependent on the combination, it also depends on the history. So timing matters. What happened in the previous cycle? What happened in the cycle before it? So that's why this timing diagram is definitely the most important part. You'll hardly ever see any truth table here. You know why? Because these components are so simple. This is a 2 to 1 mux, right? It's so simple. But with this simple component, the complexity lies in the timing diagram. Okay, so you're right. So this timing diagram will keep repeating itself over and over again. There are some other things, additional concepts that we'll learn, but this is the most part. Okay, so what I didn't cover is, and that's mentioned in the second point here, by the way. Notice a flip-flop can only hold one bit of information, Q. It's either 1 or 0. So it is storing one bit of information. So imagine you are dealing with 8-bit number or 32-bit number. How many flip-flops will you need to represent 32-bit? 32 flip-flops. So typically, in computer architecture is a different ball game altogether. There are courses here at UT on computer architecture design. So if you're interested, if you're in computer engineering, you can take them. Depending on the architecture, you decide whether you have a block of 8 flip-flops or 16 flip-flops or 32 flip-flops or 64. So you have blocks of flip-flops. You don't just use one flip-flop. This is just the basic circuit, basic building blocks. So imagine you have blocks of 8 flip-flops. That block is called a register. And we call that we have 8-bit registers or 62. So register is essentially a group of flip-flops. That's all. Are you all good? So I can use these terms repeat like, okay, positive edge triggered register or positive edge triggered flip-flop, doesn't matter. Essentially, the properties are the same. Register have just multiple flip-flops, that's all. Okay, now, this is the grand vision. Super simple cartoonish representation of the grand vision of computer hardware. Here is how different types of logics are designed across large systems. You have combinational logic that don't care about the history. You have sequential logic where history is basically the king. So here is how you design the overall system. You have combinational logic. It could be a adder, it could be a multiplier, it could be something even more complicated. And before and after, you have flip-flops. So notice FF represents flip-flop. We typically don't use latches. Honestly, we require, well, I mean, we need to know about latch because the latches are used to make flip-flops. But essentially, we use flip-flops because I just told you, keeping track of bits is easier with flip-flop. You can keep track of the edges and you can synchronize with the edges, essentially. So we always use flip-flops before and after. So this flip-flop decides how many bits to send to this combinational block. And then this next flip-flop decides how many bits to read out and send to the next version and send to the next one. So you can keep track of how many bits you're dealing with, okay? So for example, if you take some algorithm courses or maybe computer architecture, again, I'm just repeating that, you have to keep when you process different instructions, you have to keep track of how many bits you're dealing with. So imagine you have 16 bits, the first 4 bits represent XYZ. The next 4 bits represent something. The next 4 bits represent something else. So you have to keep track of how many bits you are dealing with at a time. Making sense? So you can use these flip-flops to synchronize that. 1, 2, 3, 4 clock edges. So I send the first 4 bits. This is your address. Are you guys all good so far? I'm gonna give you one like simple example here. Okay, so 1, 1, 1, 1. Say, imagine. So this is the number and 1, 1, 0, 1. Let's consider that the first bit. So you are trying to write something into a memory location. So the memories are organized in rows and columns. So at every intersection, there is a memory. Okay, it's like a matrix. Okay? So matrix has row and column. So imagine you represent, again, I mean, this is a little bit unrealistic, but it's okay. What I'm trying to convey here is, let me change the color here. Okay, so imagine that you are trying to use this bit to represent the row. You cannot use just one bit to represent row because you can only have two rows then, right? You have multiple. If you have like 8 rows, you need 3 bits. You see my point here? So there are like multiple bits dedicated to represent the row. There are multiple bits dedicated to represent the column. So imagine the first 2 digits are used to represent the row. So that means you have like 4 rows. And the second 2 digits are used to represent the column. So you know which row to go to and which column to go to, and then do something. Read the memory, write the memory, whatever, do something. So the flip-flops can help you synchronize 1, 2. Okay, so you got the row address. This is my row address. 2 more clock edges, 3, 4. Now I have the column address. And then maybe there are other numbers following it, 0, 1. That represents the data that you want to write. You might see my point here? Okay, so you have streams of binary and you can keep count of how many bits represent what. Okay, so there is a reason, you know, 64-bit Windows, 32-bit Windows, we talk about it. So in a 64-bit number system, so everything is 64-bit. So you have more information that you can pack in a stream of bit. Versus when you had 32-bit Windows, you couldn't have that many information. Okay, that's the difference. So your arrays couldn't be bigger. It has to be smaller arrays, or something like that. Anyways, I'm getting too much into the weeds here. So does this grand vision make sense to you folks? You have flip-flops before and after combinational logic, and this is called a pipelined architecture, as if you're going through a pipeline. And these flip-flops are flow controllers. They're synchronizing elements. And without them, your system will not work because you will lose track of the meaning, honestly. You have millions of bits and none of them have any meanings, just ones and zeros, unless you keep track of the numbers of the bits with the flip-flops. That's how critical these are. Okay. Why are you so sad? Well, uh, first of all, don't give up, right? I know some of the lectures, some of the concepts will be boring, more boring compared to the others. In general, education is boring, right? No, well, I would rather be hiking or biking or doing something else, or but this is essential for life, honestly. But engineering is critical. Without engineering, there is no progress in civilization. And this is basically high-tech engineering. Of course, electronics is the one of the highest tech engineering, and engineering is tough, honestly. So I appreciate your patience. And in fact, I was there not too long ago. I mean, I keep saying that every year, and I keep getting farther away from your stage. But it feels like yesterday, honestly, when I was also there, super bored at flip flops and whatever. Right? It's never fun. Honestly, it will become more. It will become more relatable, and I say to some degree fun to work with when you get into the real life and do something with it. When you make systems that are actually deployed in real life scenarios, and then you can connect everything to actual practical meaning and applications. Now, this is the difficult process. You are going through stages. You are being given a small vision of the overall thing. So many of these are boring. I remember as a kid, when I first learned about metrics, okay, like blocks of numbers. You add them, you subtract them, you multiply one matrix with the other. There are rules that you have to follow. What is the big deal? I mean, do you guys know why matrices are useful? Anyone? I had no idea, honestly, when I was just learning metrics. How you guys all know how to multiply A and B metrics, right? There are rules. You have to take a row and a column and then multiply them together. You cannot just randomly multiply, can you? Okay, there are rules. Can you multiply a 12 versus 12 cross? Uh, I'm getting there. 12 cross 3 matrix with a 11 cross 7 matrix. Can you do that? No. There has to be some matching between the rows and columns and whatnot. There are rules. So why? Why? How are they useful? Right? Again, without this meaning, and now I know why they're useful, and I'm not getting into that. Like they are basically the building blocks of your chat GPT, honestly. If you think about it this way, this is a real stretch. I mean, I'm not giving you any context here, but without matrices, there is no chat GPT. Without matrices, there is no AI. Basically, AI depends on matrix vector multiplication or dot products in terms of the core computation. And the dot products are essentially the product of two matrices. And who would have thought, right? As a kid, when I was learning matrices, I had no idea. So it was all meaningless and like very boring at the time, of course. But over the years, I feel like, oh, wow, okay, without this concept of metrics, you have no, progress in computer science at all. So anyways, sorry, I'm getting back to the slides again. So what I'm, yes,
Over the on the side again,
example of which one, sir?
like for
Yes, here, yeah, of course. Yeah. So oh, yeah, sure. Let me go over that again. So what I'm trying to portray here is that in an actual computing systems or an architecture, here is how combinational and sequential circuits work together. So far, did you learn about adders? Okay. What kind of logic is an adder? Is it a combinational or a sequential logic? Combinational. You don't care about the history. You just care about A, B, and carry in. Done. Right? And then you decide on your output accordingly. So there are many logic blocks. In fact, everything that you have learned so far had no history at all, right? There was no concept of synchronization, just taking a decision. So logic blocks, combinational logic blocks, are simply decision makers, and they make a decision based on the combinations of the input. You have a given set of bits, you select a given set of outputs. That's all. But my point is, in a large system, every bit has a meaning. Maybe the first 4 bit means something. The next 4 bit means something else. The 4 bits following it means something else. So what I was trying to get to is, say, 111001110. If I give you a bit stream like this, nothing makes any sense to you, right? As humans, we cannot read this, binary stuff. Even machines cannot do it without any specific architecture. So what I mean by that is every computer knows what every bit means. So imagine with this instruction, we are trying to write a specific information at a location in a memory block. And memories are always arranged in arrays. And the arrays are like this, rows and columns. By the way, this is the other example of a use case of a matrix. Matrix can be used to represent memory. So essentially, memories are in rows and columns. What does it look like? It looks like a matrix. A matrix have rows and columns. So you can create a matrix with specific zeros and one in certain places and send the matrix to the computer, and it will rewrite your memories accordingly. Okay. So anyways, getting back to the point. So you have rows and columns. So imagine I'm trying to write into this particular memory, and I'm trying to write one specific information. Okay. So you can do it this way. Imagine the four bits, first 4 bits represent the location of the row. With 4 bits, how many rows can you cover? How many combinations with 4 bits? 16, right? With 3 bits, you have 8. Just remember the rows of the truth table, right? So yes, of course, 16 will not go anywhere. You have many more, of course. So you need, I don't know, like 16 bits just to represent the rows, and then 16 bits just to represent the column, right? So that many bits just to represent one information, which is the row or which is the column, you see? So there you go. That's why you need so many bits. Okay, but for this example, I cannot write 16 bits and show you. So 4 bits for row. So I select the row, and then maybe the next 4 bit, 1, 2, 3, 4, to select the column. And then, okay, now I have the row and the column, so I know which memory you're talking about. But what should I write? Should I write 0 or 1? You can only do one thing. You could either write 0 or you could write 1 because it's binary. So I can give you 1 bit, write 0. There you go. So you go to that location and write 0. But my point is, to be able to do so, you have to keep track of every bit of information, don't you think? How can you count the bits? Did you see in the previous slide that you can basically control every bit, one bit at a time with one clock edge? So every clock edge will send one bit to the output. One clock edge, one bit. Another clock edge, second bit. Another clock edge, third bit. So you can control, as long as you control the clock signal, that's why it is so important. Clock is used to synchronize things. You can control the clock signal, keep track of how many edges you have sent, and then you can keep track of how many bits have passed. So you can then, hey, I sent 4 clock edges. So you have the first row. You have the row information. Then I send 4 more clock edges. You have the column information. I've sent 1 more clock edge. So you see my point here? Okay. So in a master processor, clock is everything. Okay. Notice. So just to do this 1-bit operation, and with a super simple example of 4-bit address, 4-bit row, 4-bit column, and 1-bit information, you need 9 bits. You need 9 bits to just decide on 1 bit right. And in practice, it is even more, right? Okay. So how many clock edges will you need, folks? 9. Because every clock edges send 1 bit. Are you relating to this? Every clock edge sends 1 bit. So just to, even with this childish simple example, you need 9 clock edges. So isn't that a long time? So what is the difference between 2 clock edges, folks? There is a name for it. Can anybody tell me what the name is? Time period. Isn't that a wave? It's kind of like a wave. How do you define the time period between the 2 edges, right? So this is a time period. What is the opposite of time period, folks? Frequency. Physics. Remember? So it's the frequency. So can I say it is related to the clock frequency? How can you go through the bits quickly? By increasing the frequency. If you increase the frequency, your time period will reduce. That means the clock edges will come closer to each other. And so, do you like a processor with 2 gigahertz or 4 gigahertz? Core i7 2.1 gigahertz versus Core i7 1 gigahertz. Which one do you like? I mean, if I give you the option to buy or I give it to you for free, you'll get the higher clock, don't you think? And don't you always do like overclocking? I don't know how processor, right? Why do you do overclocking? What do you increase the frequency, you reduce the time period, you bring the clock edges together, so you pass more bits quickly because every clock edge controls a bit. So it's like a bit counting game with your clock. That's how critical the clock is. If you lose the clock, you lose everything. Everything is meaningless then. If you lose synchronization, synchronization is so critical that without synchronization, bits don't mean anything. If I miscalculate one information, just notice here, if one bit is missed, you don't know what is the row, what is the column, you misread everything, all right? So I hope it makes sense now as an example. Okay, so we are out of time. We just have 1 minute. I cannot cover this in a minute. So I will stop here and resume in the next class, all right? Thank you.